Good morning, everyone. Thank you for joining our webinar today on hydrogen embrittlement and screws. My name's Chris. I will be off camera here and helping out with this webinar. But just so you know, we do have a Q&A box available if you're on a laptop. At the top bar, you should be able to see that, and you can put some questions in there for us to answer, and we will pull those and answer them throughout the presentation. So I'm going to pass this over to Andres to take over.
Hi. Hi, everyone. Hello, I'm Andres Reyes Garcia. I'm product line manager for screws and concrete anchors for Rotoblast. I'm a civil engineer, and most of what I'm going to talk about is based on my experience as in product management, both in research and development, and product development and commercialization of products. And I'm also expert in the ISO standards for ISO and European standards for fasteners. That's more or less where my background and my experience comes from. We're going to deal with the topic of premature failures on wood screws, focusing on the role of a topic that's it's being talked about a lot nowadays, which is hydrogen embrittlement. I hope this presentation is useful. I'm not a chemist, a chemical engineer, or a material engineer, so I'm gonna face the topics from a more than of an application or design and, of course, manufacturer's perspective. So this is it. This is the topic that we're gonna handle. So it's what we see here is a broken screw in a typical configuration or application where this thing can happen. So I would say that nowadays 1 out of 1,000 projects, that's more or less the rate that we handle with the information that we have. We can have that in 1 out of 1,000 projects or building sites, we have experienced some failures of screws. We experience at least one failure. Most of them are minor, but in isolated cases, this can be relevant, significant, and of course, I think to handle, we are going to focus on the cases of hydrogen embrittlement, which this picture more or less tries to evocate. As you see, there's a thick metal plate, there's a wooden element, so wooden substrate, but there are some other factors that come from the environment. You see as well, there's a little bit of moisture, of water, and there's some corrosion present in the screw. And we're going to talk about all of these factors because we'll try to understand how it's necessary to talk about hydrogen embrittlement in the context and having these factors into context within the context. So let's take a step back and give an idea on why this is relevant now. So 10 years from today, I think a little bit more, buildings were a lot smaller, or at least what's considered common timber engineering was smaller, and it has been growing a lot in time. So we see here a hybrid building with concrete, steel, and wood, with big elements in these dimensions. Now is commonplace, where 20, 10, 15 years from now was not. And of course, these buildings are requiring more and more efficient and performing connections. That means bigger connections. That means as well more steel into the connections, bigger metal plates, which bring a lot more stiffness as well in the connection and brings the criticalities of installation as well. Enhance the criticalities of the installation. And many times this means as well longer construction sites for the timber buildings, which means as well more exposure to environment. So putting these things together could eventually, not necessarily, and we're gonna get into that, but could lead to failure. In some cases, that failure would be um, the name of that type of failure, of the mechanism for that failure, would be hydrogen embrittlement. So some examples of where the construction, from small houses today, this is commonplace as well. So this is the sizes of the buildings that we're talking about, and more and more are becoming the commonplace in the sector, and also the robustness and the um, magnitude of the connections. So when a premature failure happens, many things can be can be evaluated, have to be evaluated, and can be the reason or the mechanism for the failure. Some could be more related to production or product criticalities than they are, and are related more to the manufacturing of the product. And others can more be related more to application or in-service criticality, or the management of the factors that are that happen in the construction site. Uh, to get a broader understanding on what we understand as premature failure, this is this chart here. I gotta say, I made this chart, and I'm still understanding if this chart works for everything. So, but I think it works more or less for. It explains more or less the challenges, but it's rough. It's still rough, and it can be improved. Nonetheless, uh, we have this could be all premature failures. I mean, I will not consider, I will consider them premature, as they will. We're talking about a failure that happens before of the end of the service, of the design service life. So after the design service life, every failure, let's say it's or the life of every fastener, or everything that can break, has our let's say has been overpassed. So it wouldn't be considered premature. But from the day zero, let's say the day we installed, we're talking here about fasteners. We installed the fastener to the design service life. Many things can happen, and the environment and the context change. The context changes. So the first thing that can happen is installation overstress. We can overtorque a fastener during installation, and that, of course, would mean that we are above the design capacity of the screws, and it break. It will break in dry conditions, and it will break because of an overstress. And that can happen. That happens, especially if we add improper installation angle with an impact wrench, so an uncontrolled torque, installation torque, that can happen. And in that case, we're above the design capacity of the screw. That happens instantly. Or will as well add some tensions to the screw that would then mix with other factors that would lead to failure. One of those would be internal hydrogen embrittlement. Internal hydrogen embrittlement, we will talk about this in more into detail, but it happens from hours to days, even could be even weeks, but generally from hours to days after installation. And this is more or less the stress compared to the design capacity of the screw that it requires to break. So we're talking about a premature failure where the load of the screw is on the screw is a lot lower than the design capacity of it. In the same period, in the period of days, we start in the construction site. We can start having exposure to moisture or humidity, and we can add the overstress that maybe was not enough to break the screw, adding swelling, adding the swelling of the wood could lead as well to breakage. In this case, we're talking as well over surpassing, say, the design capacity of the screw, and that could lead to breakage. Finally, in the building side, what we can have, and that happens from days to months after installation, it's environmental hydrogen embrittlement. We will see it in more detail, but it's the other type of hydrogen embrittlement. And in that case, We could be talking about a fastener, a breakage that happens um, below the design capacity of the screw, but also above the design capacity of the screw. We're talking here about a combination of factors that could lead to failure above and below. After the building site is closed, and this is very important, these factors, I mean, both internal and environmental hydrogen embrittlement are, at least this is what the literature states, um, can be excluded. Most of cases can be excluded. I would say maybe just a little bit after the building site is closed, because they depend on the conditions that need to be present. In the case of environmental hydrogen embrittlement, corrosion, for example, is a very relevant condition. And when the building site is closed, exposure to moisture generally is stopped. So in that case, we could stop talking about environmental hydrogen embrittlement. So after, in service conditions, then we can have a breakage because of accidental or catastrophic effect events, or corrosion happening. Sometimes we are, for example, in wet conditions, because the project is in wet conditions, or the fastener is exposed, and that corrosion itself can lead to failure. Fatigue as well, uncontrolled fatigue, unintended or unforeseen fatigue can as well lead to failure on time. And there are many other factors in service condition that could lead to failure, but I'm not gonna, we will not focus in those. These are the ones that we will focus the most. These are the ones that are, that we are talking, that the people is talking about, and these are the ones that are right now under the radar, and we're gonna focus here. So I introduced some of these concepts like briefly before, but these are the three main factors, that need to be present for premature failure to happen. This not necessarily together, but together together as well. So stress, if stress is present alone, as we talked about before, can as well lead to failure. So when we talk about stress, we talk about over torque or improper installation angle or accidental loads. So this, for example, a dry case of breakage of screw. In this case, it's an experimental campaign that we conducted, installing the screws at different inclination angles. So with uncontrolled torque. In this case, we are talking about the combination of these two factors and how they will induce a breakage in absence of a hardness or of a material criticality and of a moisture criticality. So this can happen. Or accidental loads, because accidents can happen. This is not a case that happened in a project that we were in. This happened years ago. I just found it in YouTube while doing the research for the presentation. But I don't know, but something can happen in the construction site. A crane can lose the hooks, and the load can fall. And as it happened here in Massachusetts, this can lead to breakages, of course. So this is just one of the many things that can happen that regard accidental loads or unforeseen events. But this is a type of event. Right? This type of event. When we talk about moisture, moisture or humidity has two consequences. One is corrosion, and then we're going to deal it apart. And corrosion itself, of course, can lead to failure all alone, because corrosion means, let's say, localized or surface corrosion. Means that the section of the screw will eventually lower and lower its resistance section, becoming becoming too small to resist the loads for the design loads. So in that sense, it would fail. It could fail alone, but it could fail also together with stress. And the other factor is wood swelling and shrinkage, which would add a stressor. In the case of corrosion, it's relevant in this case, and it's very relevant because it would lead to hydrogen absorption as well, and would eventually, this type of hydrogen absorption is what we will call environmental hydrogen embrittlement or external hydrogen embrittlement. We'll get to that. And as I introduced, so the wood swelling and shrinkage is actually a consequence of moisture, but that it's actually included, will need to be included into the stressors that could lead to failure. Finally, the material. Some conditions of the material can as well be considered as factors that could facilitate some mechanisms to happen. So in generally in wood construction, when we talk about fasteners, we're talking about screws or any type of fastener above 1,000 megapascals of strength. And in that case, they are they're high, or what's considered high steel, high strength fasteners. And for those type of fasteners, attention needs to be paid to the core hardness, and not only core hardness but also surface hardness. Core hardness is the parameter that it's used the most, let's say, or limited the most in standards. Coating thickness, continuity, and absorbed hydrogen. So controlling all of this is fundamental. Of course, the material itself, it's not a cause of or a trigger for failure. That you won't open a box of screws with a broken screw because it broke because of any of these things. But it could lead the fastener to be more or less prone to failure in the presence of these two other factors, moisture and stress. And when we're talking about these three factors together, then we were talking about hydrogen embrittlement. Specifically, not necessarily moisture, but specifically hydrogen. I mean, like the most proper way of talking about this parameter would be in terms of hydrogen, because not necessarily does it need the presence of the moisture. Hydrogen can be absorbed all along in different forms. What is it? This is the definition that's given in the ISO standard, the ISO technical report 20491. So this is like the most relevant definition, or the most scientific one, and very synthetic. So it's the permanent loss of ductility. So it's a loss of ductility in a metal or alloy caused by atomic hydrogen in combination, always in combination with load, and which can be induced or reduced or residual tensile stress that can lead to a brittle failure after some time. So these factors are necessary. So we're talking about a loss of ductility in a metal caused by atomic hydrogen, the presence of atomic hydrogen. That means if there's no atomic hydrogen, then there's no hydrogen embrittlement. And that means as well that there's always a load needed. How does this happens in many processes that can be during manufacturing, and that can be also when the screw is in service? Hydrogen from outside can migrate from the exterior to the structure of the fastener, and then it can accumulate in the grain edges and in some parts of the structure. And then when the screw will be put in tension, or any type of force of tension is just what it's translating into in this case, the hydrogen will try as well to move to try to reach the surface. In this movement, then the hydrogen will assist the creation of cracks in the structure of the screw. Then that's what we will call hydrogen-assisted cracks, HACs. What does that look like? What we see here is a screw that was broken by torsion. So it's like a dry test with immediate torsion, just like screw around, and you see here, so this type of smooth curve way. So you see the pattern here, and it very much talks about a torsion breakage. There's also the presence of this I don't know, I'm translating from Italian, but it's like a tongue, no, like a sort of reduction in an elongation in one of the sides of the section that it's very typical from ductile breakages. When you have a hydrogen-induced breakage, it would look more like this. So it's very perpendicular to the axis, very clear cut. You will see a different pattern. Okay, you see not the curves and not that much of an elongation, no, like we see before. And depending on the type of hydrogen embrittlement, you will see strong signs of corrosion as well. Okay, so that is a very strong symptom of hydrogen embrittlement. If you take a look a bit further, you will see as well that the structure inside of the, I mean, let's say if you take a look at the sections in some part, let's say in some small pieces, you will find in the brittle failure, in the one that we saw second, this type of structure. And this is what we call intergranular cracks. So it's on this grain formation, and this is a symptom of a brittle failure. This doesn't necessarily mean hydrogen embrittlement. This means a brittle failure. And finally, at the right, what you see is ductile behavior. So this is a microstructure of a ductile type of failure. The first one is more of the typical breakage that you will see as well when there's some hydrogen embrittlement. That doesn't mean that if you find this, then the cause of the failure is necessarily hydrogen embrittlement. Doesn't. But putting it into context, analyzing it all together, this is one of the things to take into consideration when determining the mechanism of failure. It's important to say as well that once a crack is in place because of any factor, because of incorrect installation, because of a bending of the screw as well that comes from incorrect installation or some unexpected loads, the presence of hydrogen would then assist the formation of the crack. So this, depending on the independently on the source of the crack, then hydrogen, in this case, would be the number one. The hydrogen will then assist the completion or the advancement of the crack as well. And that's hydrogen embrittlement. So let's go back to the sources of hydrogen. Where can hydrogen get inside of the material of our fastener? So this is from a research by Graz University, and they measure the hydrogen inside of the screw after every production process. And you don't need to know every process, but there are some of them have more or less influence on it. And more or less, we can summarize it in the pickling process, which is the phase that from it's a phase from the cold forming to the electroplating process, an intermediate phase, and that's the one where hydrogen absorption is the most affects the most, influences the most. Then the electroplating itself can also add hydrogen, and finally the heat treatment process can as well induce some hydrogen, but it's a lot less. Let's say we put those three main phases in the processes. This would be the most and less important. What do we do? So what generally manufacturers or even Rotoblast does. So to tackle the hydrogen, the absorption of hydrogen during production, there's a need of incorporating inhibitors in pickling, in the pickling baths to suppress the hydrogen generation. So no hydrogen is generated in the bath. And then as well, for some sizes or in general, like the embrittlement baking, so a baking process at the end of the production can also facilitate the escape of the hydrogen inside of the fasteners. We do it for some sizes of screw as well. It's part of our production standard production. Then storing screws in dry control environment, and finally performing ISO 15320 continuous load testing. Those are the testing that will tell us, okay, there's some or no hydrogen. So of course it's a certain amount of screws per batch that are put into 48 hours of continuous tensile load, which would simulate the conditions for breakages for hydrogen at a 80% of the ultimate capacity, and that would tell us if there is in the process of manufacturing there is some hydrogen induced into the material. But I gotta say as well, this is pretty much state of the art of the industry. So of course it needs to be done, it needs to be checked, it needs to be controlled, and that's what Rotulas is doing. But I would say that that's state of the art of manufacturing in general among the producers of fasteners. Core hardness, which is the other factor that we will discuss, and you will see that it's becoming more and more present. So core hardness, of course, is how hard the screw is in its core. You generally measure it by using a micro hardness. There's beakers and Rockwell methods to measure the hardness at the center, at the nucleus of the screw. But what we see here is a relation between hardness and hydrogen. Sorry, resistance, hardness, and hydrogen presence, hydrogen presence. So if you consider that this is a sample cloud, so all of these are fasteners that were tested and gave these results, and they were like summarized into a cloud. What we have here is all of the samples that are in this campaign were hydrogen rich. They were enriched with hydrogen, and the variant of what will vary would be the hardness on them. So you will see that with the same amount of hydrogen, say, the resistance which we have in the y-axis, the resistance will change. The ultimate capacity will change a lot depending on the hardness. So once we are having trouble with the pointer, once we are above the 390 threshold, you see here a decay on the performance on the tensile capacity in this case of the screw. So you see here a very strong change on the behavior of the fastener, and that means the core hardness tells us how susceptible is the fastener to the presence of hydrogen. Again, we can have a 500 beakers fasteners, and without the presence of hydrogen, it will not fail because of hydrogen embrittlement. Of course, you need hydrogen for hydrogen embrittlement. Nonetheless, if there is hydrogen, the higher is the hardness, the more susceptible it is to failure from hydrogen embrittlement. And that doesn't mean either that you cannot have a hydrogen embrittlement mechanism for failure with screws that are below 390. Okay, that this is only a this just means that the risk is becomes closer to zero. Let's say it becomes less. So
Andres,
what? Yeah.
I have a few questions for you. So one, have you seen any of these failures in wood-to-wood connections or just steel-to-wood connections?
In my experience, I have seen it In wood-to-wood connections, yes, but in a 1 out of 10 ratio, more or less, even less, 1 out of 20, maybe 1 out of, yeah, that would be more or less my experience. And that's because the conditions for failure, of course, the bigger the load, the higher is the risk of failure, and that changes a lot from wood-to-wood connections to steel-to-wood connections. We will deal with that also in some slide going further.
Right, and then
So
another
yeah,
another question. So you said the ratio is 1 out of
20, but even more. I will really 1 every 20 failures. I would say 1 is wood to wood, and 19 is steel to wood, and not even steel to wood, thick steel to wood yeah, that in my experience. Yeah.
Okay, that's great. And another question, what is the core hardness of the screws on average before baking and after baking? And how long is the baking for?
Okay. So baking, just to start with the final part of it, baking takes from 4 hours, can take from 4 hours to 16, I would say, to the highest I've seen in the industry. This is what I'm talking in general, not about wood screws only. But I don't know, washers can be there are some of them require 4 hours baking. And depending on the criticalities of the production process, you will maybe need some 16 hours. In general, I would say in the wood manufacturing industry, it's around 8 hours. The baking, that's it, more or less the general use. But it could be less and it could be more. Not less than 4 hours. Definitely, the effectiveness of the baking doesn't is not that high.
And does the hardness change between before baking and after baking?
Yes, and it doesn't. Hardness is affected from I'm going to go back there. It's affected from 200 degrees Celsius above, or 395 Fahrenheit above. So dehydrogen baking has to be strictly below 200 degrees Celsius, so that it doesn't affect the hardness and it doesn't affect the microstructure. So a baking that it's done above the 200 degrees is not a baking, it's a heat treatment process, and it would affect the final performance of the screw.
Okay, no, that's awesome. And
yeah, and the mean hardness before and after. So this was actually very close to what I was going to talk about, which is what is the industry, what can you find in the market. So generally from 300 to 550 liters, there are some reductions of something that it fits between these ranges. I'm talking not only about wood screws, I'm talking about automotive and about steel frame industry, or just pieces for DIY. Nonetheless, the norm establishes and the standards approach it's to set two thresholds, one in 360 and one in 290. 390 above would be considered as high risk, even if not necessarily as we see here today. Right above 380, there's a huge, not necessarily a huge change, but of course we see here the performance, the decay of the performance. So it's understandable that there is a threshold in 290, and the other threshold is 360, where below 360, the norm says that you could, the risk of hydrogen embrittlement is so low that in many cases, depending on what you're producing, you could even have no control of the of hydrogen embrittlement parameters. So what am I talking about? In these are the two standards, 4042 and 2702, that regulate the hardness, depending on the first one on internal hydrogen embrittlement, and the second on external environmental hydrogen embrittlement. And as you see here, below 360, you could or have supplemental process verification with regard to internal hydrogen enrichment, or product testing, or baking, and the norms even says at the choice of the manufacturer. So you have then this range here below 360 and 390, which is more or less a acceptable risk range. And here the norm talks about supplemental process verification and product testing and baking. Above 390, then we're talking about necessarily having all of this. So process verification, baking, and product testing for each manufacturing lot. So it becomes more and more strict. But you see here that for internal hydrogen enrichment, you can have products that are above 390 beakers, even 500 beakers. But the important thing is that after the screw is produced, the fastener is produced, then you take out the absorbed hydrogen. Well, how? Baking it necessarily, and then checking that the baking was done properly, and then there is no hydrogen inside. But on the other hand, for environmental hydrogen enrichment, which is this norm, there's a limit at 290 beakers. So just a second here. Okay. Because it depends on the fact that we are exposed to hydrogen, we will be exposed to hydrogen. So we could have a fastener and install a fastener above 380 beakers, even at 500 beakers. If we are sure that it will not be exposed to any type of hydrogen, then we will have no problem. Nonetheless, if there is a hydrogen source, then ISO 2702 would limit to 380 beakers. And that's just talking about 2702 and 4042, which is the production standard. We will talk about the science standards in a while when we will get to the CSA and the Canadian standards and why do they establish as well some thresholds. I think I answered the question, Silvia.
Yes. I do have one more. Like, besides keeping the screws stored in dry conditions, what is the optimal storage environment?
Optimal storage environment. It's concerning hydrogen embrittlement. It's any environment that wouldn't expose them to corrosion and or to a source of hydrogen. So the dry condition would limit the entrance of atomic hydrogen, but would also block or stop any possible source of corrosion. So this is what we try to avoid, and this is why it's important to store them in dry conditions. So keep them dry and keep them unexposed to sources of corrosion, which could be also salts. Could be also if there is an acid environment, somehow it's an open box in a brewery. I don't know why, but that could happen. They are exposed to those factors, and then they will be more prone to corrosion and thus to hydrogen embrittlement when in service, when applied.
Okay. Perfect.
So, as I said before, and now as you've seen, for internal hydrogen embrittlement to happen, or a failure caused by the internal hydrogen embrittlement, the moisture is doesn't need to be there because the hydrogen is absorbed in the manufacturing process. So it's more a material condition right after the production process, after manufacturing. But what's necessary as well for failure is stress. Of course, as I said before, the screw doesn't break just by taking it. So a minimum stress needs to be present. And in general, it is with installation torque or an improper installation angle or accidental loads. The higher the stress, the higher the possibilities for hydrogen embrittlement failure to happen if the material conditions are met. And also an important thing is that it happens, as I said before, from hours to days after installation. In contrast, environmental hydrogen embrittlement requires moisture to be present, And it requires all these factors to be together. So we have a material condition. It's given by the core hardness of it. So the material is susceptible to hydrogen, even if there's no hydrogen inside. Well, yeah, that's why sort of hydrogen is out of the picture. There's a stress, and the higher the stress, the higher the possibility. Also, because with installation torque and improper installation angles, you can create a crack in the coating that then would lead to corrosion. And with this corrosion, in the presence of a moist environment, which is generally present, then we would have environmental hydrogen embrittlement. So this is more or less the full picture of all the factors that can lead to environmental hydrogen embrittlement. And as well, in contrast to internal hydrogen embrittlement, this takes from days to weeks. Let's talk about this single, about each one of these forms. Oh, so I already introduced all of them, but let's give them a deeper look. Stress. What can be a stressor? As I said, over torque, improper installation angle, accidental loads, wood swelling. And what does it look like in a construction site? More or less like this. So you see the marks here of, there were many things done wrong here, but these are the ribs of a countersunk head after a very strong installation, torque applied. And you see how the cylindrical hole that there would need to be a cylindrical hole is no longer cylindrical because you see a counter, it starts getting countersunk. And here it could be a mix of improper installation angle and over torque. You see here, this is another construction site. You see how a screw, in this case, it was inserted with 13 degrees. So these things happen. This is what they look like. And it's not even that bent. If you've been in a construction site, you see that, you know that this from time to time can happen. But this, especially when some to over torque, can lead to weakening the screw. The best case scenario, weakening the screw. Or other cases scenario, they can fail. In many cases, coming to corrode to over torque and proper installation angle, you could even see the corrosion signs. In this case, it's not yet the rust or the what some cases that you see here, but red corrosion, but white corrosion is present, and you see the phenomena starting to happen. Finally, wood swelling, as well as a stress factor. It depends on here. We need also moisture in these cases before. We don't even need more. Well, there's corrosion, there's moisture, but we don't even need moisture for this to be even a case. And in these cases, this is also a case where we're involved. There's also wood swelling. This is proper installation angle. Wood swelling, the signs of moisture here happen. We have done some research on the installation influence. So of course, a question that comes to mind is, okay, how big is installation problems in the failure? So how critical is it installing wrong screw? So we have done some tests with here. This was with Karlsruhe Institute for Technology, and installing screws at a different angle, asking the question, so can we recognize that the screw is not screwed at the correct angle? Finally, does the bending from an incorrect installation can lead to affect the capacity of the screws? And we're talking dry conditions. We're not talking here about moisture or hydrogen embrittlement, just breakage. These are the results. When you screw at the recommended torque, you see that even at 80 degrees, so a misalignment of 10 degrees can be recognized easily. Okay, then of course at 70 degrees and more than that, it's preposterous, I would say. But this is more or less what a 10 degree would look like. Once you get into tightening after the recommended torque or over the recommended torque, in many cases you won't be able to see the difference between an 80 degree and a 90 degree because the screw bends and the surface of the head gets fully in contact with the surface. But what can happen, and that is that they break even during the installation. Of course, the higher is the inclination, the higher is the possibility for breakage. And here you see also as well 40 degrees and 45 degrees, 50 degrees, okay, the breakages are easier to happen, of course, because it's unreal, I would say, inclination. Nonetheless, these ones that are the most relevant, you see how the effect. And you have some plastic deformations as well on the screws. When you screw them with an inclination angle, that means that there is an effect on the tensile capacity that we will see as well afterwards, but also definitely there could be some micro cracks in the structure of the screw and micro cracks in the coating that could lead them to corrosion, and they would favor hydrogen-induced cracks and hydrogen-induced corrosion, hydrogen embrittlement. This is, so to answer the question, how much bending can affect the tensile capacity of the screws, this is our results. Depending on the angle, on the means, yeah, 90 degrees would be perfect angle of inclination, and this is 10 degrees of misalignment, 20 and 30. So you see how the performance changes from 100% to 70%, depending on the installation. Of course, 60 degrees is a lot. I really expected it to be more impactful, but we're talking here about dry conditions. So we know here from this, we know, okay, installation can have a permanent effect. Improper installation can have a permanent effect on the dry performance of fasteners. Let's see as well when we put it together with other factors. So let's add moisture. Let's talk about moisture alone. We need to talk about moisture because what we see here is real pictures from real building sites. And of course, we have seen it. We're not talking about the service conditions of dry design, of dry sites. We're talking about construction site conditions, and these can be real. These can happen as well. And when these type of things happens, this means as well that the connections where the water tends to drain and to concentrate are the ones that suffers the most. So the conditions here, at least and it could be a very long period, it's very hard to say that they are dry conditions. So we're talking here about an exposure of the connections that can be very, very aggressive. And finally, here as well, we see them the interaction of all those factors. So we have thick metal plates, we have improper installation, because you see here that there's at least 10 degrees, and the presence of moisture. So this is the most number. This is a typical case where hydrogen embrittlement can happen. And if there's moisture, of course, there's corrosion. Let's talk about corrosion. And then hydrogen absorption through corrosion, which the proper term would be cathodic hydrogen absorption. There are three types of exposure that we need to talk about. So the first one would be the atmospheric exposure. So how aggressive is the environment? It would affect mostly the exposed part of the screw. I wouldn't say this is not relevant, but this is less relevant, as we saw in the picture at the beginning of the presentation. The corrosion tends to happen in these type of failures in the inside of the screw. So we generally, in this case, we need to be more focused on the wood corrosivity classes. So how aggressive is the timber where we're putting the screw in? In these cases, it's also very relevant the service class or the exposure condition, where it's a dry or wet condition, which will tell us as well how humid is the atmosphere, and then the moisture inside of the wood. So at the end, we will have an interaction of these three categories. At least in the European approach, the ISO standards talk about a C1 to C5, being C5 the most aggressive, while European standard is the current norm, that the only norm that gives a categorization on wood aggressiveness, and gives categories from T1 to T5. And finally, the service classes in the European standards go from service class 1 to service class 4, whereas North American standards tend to have only a dry wet conditions. That's with the threshold in 19. So this is more or less what service classes look like in Europe. And they tend to, at least the new approach in the new Eurocode will give an annual average for the what would be, let's add here, what would be considered dry condition or service class 2, an annual average of 16% and an upper limit of 20% that cannot be surpassed by more or less 3 to 4 weeks. So 16% should not be surpassed for more than 2 or 3 weeks, and with an upper limit of 20. So this is more or less the context of where to consider a dry or where to consider the wet condition. Corrosion classes of atmospheric exposure are defined more or less from the distance to the coast, being salts the most important agent for atmospheric corrosion. Not the only one. You have, for example, sulfites can also lead to corrosion if you are close to industrial environments. But the most important, at least for residential, is definitely the distance from the sea. So this is a thing that needs to be considered when choosing the material and knowing which is the corrosion risks. But coming back to the importance of timber corrosion, what you see here, I'm sorry about the Spanish, but this is from a consultancy that we dealt with, and it helps to illustrate how powerful could be timber corrosion. So here in this case, atmospheric corrosion is not an issue, as you see here. I mean that in general, both the bolt, the nut, the fastener, and the plate are doing good. But when you take out the wood and you see it from below, you see that this is a matter of wood corrosion. So see how the internal part of the screw is affected, and if there is the material susceptibility and the force generated by the load of the wood, the conditions are met for hydrogen embrittlement to happen. So European standards will have this. This is an extract of 4592 standards, and they introduce these categorizations where there is a limit between what can be considered as dry and wet. So T1 and T2 is where we generally consider as standard conditions for buildings. So a residential, at least for design, a residential building where everything is closed, it's generally considered in the project as T1 or T2, where there are some cases where you have exposed conditions where you start needing to consider the species of the wood, and depending on the type of the species, it would be more or less aggressive. So the norm states that at least from 16%, it becomes relevant the type of species in the environment inside of the wood. And that, of course, will affect the type of fastener that you should use to withstand that condition. The other important thing here is this is the service threshold. So we understand that from 16 above, then the aggressiveness of the wood starts being relevant. And that means that if the construction conditions where these elements are exposed, where the wood is exposed, could lead to an environment that can lead to corrosion, and that can lead then to exposure, to the generation of hydrogen. We did in the Smart Book, we did a sort of database of the pH of the species, so that you can easily identify by knowing the species of the wood which one is T3 or T4, so more or less aggressive when exposed to moisture. So in T3, we generally find the most common species: spruce, larch, and pine. While in T4, you generally find hardwoods like oak. Oak is very aggressive, but not only you find as well Douglas fir. Douglas fir has, when exposed to hydrogen, to moisture, has an aggressive environment inside, or thermally frigid beech as well. So depending on the service classes, you will have different corrosion rate. So from up to 10. This is why also service classes make sense for electroplated screws. This is based on electroplated screws. So you see here is corrosion rate of zinc. So in service class 1, so up to 10%, corrosion rate is very slow. When you get to 16 as well, you have minimum corrosion, but it's almost not significant. When you get into service class 3, you know there's corrosion. You know corrosion is there for and it's present. Service class 4, corrosion is very high. And I will get back to this slide just to give you an idea. So above 20%, and 20% is not that hard to be reached in many construction sites. The norm tells us that every species is very aggressive. So every species is a T5 when above 20%. And just to give you an idea, in T5 conditions, only for design, the prescription, the norm prescribes that you should use stainless steels A4. Okay. So what does an evaluation of the corrosion looks like? This is, for example, the marble molding project in Copenhagen. So this is in the coast. This is the seaside. So these indoor spaces can be considered as T1 because of the moisture content, while these outdoor parts or protected or exposed could be considered as T3. This is a spruce mainly project. So this is more or less the conditions of the timber in this project. In this case, we're talking about atmospheric corrosion. Indoors, of course, we're in C1 class, while exposed parts would be in a C5 because we're very close to the sea. So this is more or less a very rough case of evaluation of the corrosion conditions. That leads to the proper material selection. So based on that corrosion evaluation, it would be required. So let's say the proper next step would be then to choose the proper material according to that to the environment. So what we do in the smart book and in our catalog is just to tell you which is the corrosion capacity of each coating or each material. So zinc plate, it's T2, C2, while organic coatings can go from T3 to C3 and so on. Stainless steels, for example, an A4 is T5, C5. Okay, so this is the tool, let's say, that we give once you know which are the conditions that you will have to choose the proper product. It's not the only thing to consider. Of course, there's as well galvanic coupling. Galvanic coupling can happen, and this picture is not the best, but it illustrates corrosion happening around the screw. It would indicate that there's a difference in the metals, and thus this is galvanic coupling. Galvanic coupling only happens when these three things are present. Different metals. If the metals are not different, there's no galvanic coupling. The presence of an electrolyte, so indoor connections, even with different metals, generally don't have any problem unless there's water. And direct contact. If there's no direct contact as well, there is no galvanic coupling. Galvanic coupling happens and it's stronger depending on the material. So the further away in this graph you have two materials, so the quicker this the galvanic coupling will be. And in some cases, the galvanic coupling is that slow, that low, that it can be deemed irrelevant. So, for example, we do offer many solutions that are use aluminum plates with zinc-plated screws. And they are different materials, but the difference in galvanic coupling is that it's not that slow, that the corrosion is very, very slow. So it's almost irrelevant. So we consider, let's say, within the context of the design service life, you can even not consider it. So that can happen. And what can you do? You can disconnect the joint, the electrical joint. Of course, you can use similar methods like zinc and aluminum. You can coat them or like varnish one or the other. That way, you will cut the conduction, and or you can use like a tape. So controlling moisture or interrupting the direct contact. This is what it looks like as well. So this looks like having a screw that it's more resistance than the plate or the washer in this case. So finally, moisture not only leads to corrosion, but leads to wood swelling and shrinkage, which is a stress factor. We know that Egyptians used to build the pyramids or to cut the stones that used to the pyramids by putting some wedges on them, or like breaking them and putting some edges and then wedges, and they would break apart. So we know that wood swelling can be very powerful. We know that wood swelling, we know how wood behaves with water. We know how much it deformates. It depends on the elasticity models, and it depends on many factors, of course. But we know that the maximum deformation we will get it at 30%. So 30% of bound water, there's no more deformation. We know as well that depending, you have a linear deformation, a tangential deformation, and a radial deformation. That would then mean that a beam that it's 4 meters, and with this section, you could have increases of 5 millimeters, 3 millimeters. So it could be irrelevant. What we know less is the interaction between wood and the connections. So how the stiffness of the added stiffness of the plates and the screws inside can then affect the connection, how much load can then be introduced into the connection. So we know that the screws are affected differently from this deformation. So we have a part that is in a drier part of the beam, while other one can be in the wetter side of it. So we have a differential deformation that then can lead to an added stress. How big can that be? So we use the formula currently in the DIN standards, like very, very roughly. We could even get to 55 kilonewtons, that it's close to the weight of an elephant, but that's too much. That's overestimated. And there are some models that exist that can help us at least give us a first approach into the added strength. If we do this type of testing, like adding load cells, putting some load cells and putting this type of sample into water, we would be avoiding, not considering the stiffness added by the screw. And in this case, we will have more or less 800 kilograms, which is almost 2,000 pounds of tensile force, which is relevant. Not that big, but nonetheless, it's not zero, so it's important. What if we put, and we ask ourselves the question, can we break a screw if we via wood swelling, or via wood swelling and improper installation? So we put many samples into water, samples with the correct installation and samples with inclination, with over torque, and also adding some damping solutions like a soundproofing profile. So in the cases of over torque, this is just a case of over torquing with an impact wrench and stopping when let's say when the screw gets into contact. That way we will add a lot of added torsion. And this is one of the cases of inclination. In one case, we took it out to the screw out, and you see with not that big of misalignment, you could even perceive the bending, the permanent, the plastic deformation of the screw. So this is the final results after 6 weeks. This is what they look like. The thin metal plates have this type of deformation, which is considerable, but you see that even the plate deformates. So that means that the screw doesn't take all of the loads of the deformation given by the deformation. In these cases of thick metal plates, you see that here the metal plate didn't move. So in this case, the deformation was a lot of it, or more, let's say, than in the thin metal plate was absorbed by the connection. And finally, damping solutions, you will see here the effect. So it helps us perceive as well the effect of the wood swelling and how present it is. So the results were that with correct installation, wood swelling didn't break any case. When we add misalignment, when we add over torque, then when we reach the 30%, more or less, we're in the range of reaching the 30% of moisture content, then we had some breakages of the screw. So and of course, in this case, it could have happened that we are adding the moisture factor as well. So environmental hydrogen embrittlement can be a mechanism here. But it's very interesting because even if environmental hydrogen embrittlement could have been an issue in this case, because there's moisture, there's stress, and there is could be a core hardness, a susceptibility of the material, let's say, they didn't break because the strength, the stress side was not enough. Didn't reach wasn't enough for them to break. While in this case, it could have been as well that with the improper installation angles, with the bending of the screw, you start having some cracks and you start letting corrosion happen. And environmental hydrogen embrittlement could have been an issue here. We currently know, so from this test, we know that they can break. We currently know after some research we are doing with the University of Alberta in Canada, preliminary results tell us that over-torquing plus the swelling effect can lead to even 65% of the tensile capacity of the screws. So they are very relevant, and these are the preliminary results that we have so far. So conclusion here, the design process generally considers only the force assessed during the design phase and the resistance of the screw given by the manufacturer. We now know, we know that there can be an over torque force during installation, and there can be a force due to a swelling of wood by water. And these two, of course, needs to be reduced as much as possible. It needs to be considered. It needs to be an added safety factor. I don't know exactly. Of course, there is some safety factors in some standards like the K mode in Eurocode, but a precise safety factor for load force that it's linked one-to-one with the load force with swelling and by over torque needs to be considered. Of course, with correct installation, we reduce the over torque, and in the design phase and with the moisture control plan, which is the most important, we can also reduce the effect of wood swelling. I need to go a little bit faster. We saw all of this, of the effect of all of this together, and of course, mitigating the risk of breakage or failure from environmental hydrogen embrittlement needs to tackle all of this. One, let's say, or all of the combination of these factors. Not only for environmental hydrogen embrittlement, but and I need to highlight this, to avoid premature failure. I think at the end of the day, we don't care, or you don't care if you're a designer or a constructor, if it was environmental hydrogen embrittlement or not. What you care about is that they don't fail. So these are the things that need to be considered. In the case of environmental hydrogen embrittlement, these are the three parameters that we saw before, and the lower the sustained tension of in the connection, the lower is the risk of hydrogen embrittlement. The lower is exposure to hydrogen, in this case moisture, the lower is the risk of environmental hydrogen embrittlement. And finally, the lower is the fastener hardness, so the susceptibility of the fastener, the lower is the risk. So we can act in one, depending on the risk of the connection, or we can act in everything, depending on the importance of the risk as well of the connection. So what we have seen, and I answered this in one of the questions, is that these type of failures happen in metal to wood connection, but also in connections with high density or low swelling wood. For example, LVL or plywood with CLT, where you have a very strong difference in the stiffness one and in the reaction to moisture. So how they deform and shrink and swell. Then you're adding as well the stress factor and the moisture factor and now you're acting in the stress factor, and they can lead as well to failure. In those cases, I would say that 98% of the failures that we have seen happen in conditions that it's hard to be considered. They need to be considered as wet conditions. They're talking about the building site with the presence of a high presence of moisture. So what can be done? I'm not going to get into too many details, but these are things that can be done during design. So using damping systems, prefer larger diameters than smaller diameters. Distributing loads. Avoid, of course, using details that prevent water stagnation. And of course, putting in the design specs, the correct installations given by the manufacturer as well, and also protecting the installation from during the construction site. I'm not getting into the details of this slide, but this is a slide that you can use. You can pause and see what can you do in every level. So from fastener selection to the design of the connections, selecting the appropriate hardness level, so asking the manufacturer for the hardness levels, using torque limiter tools, so controlling the installation and preventing water being into the construction site. We give in the boxes of many of our screws an installation manual, so concerning installation, respecting the installation instructions given by the manufacturer. Will be as well concerning inclination. What is the tolerance? This is a common question. What is the tolerance with the angle? There is no norm right now that gives a tolerance, a clear tolerance, but we'd say 5 degrees would be acceptable. Then from 10 above, we start having problems. The only relevant standard that we found was for concrete screw, the ACI 355 gives more or less 6 degrees for concrete screws. And there's not that difference. In the concrete, there's no such difference between the materials, the connected materials. While the wood screws have a more critical condition. So avoiding as well, as is examples of correct installation. And we're going here into one of the most important topics, which is moisture management, a moisture management plan. So preventing water to the water stagnation, allowing water to drain, and allowing the building side, the connections to dry as well in time. So protecting them and draining. This is very, very, very critical. I would say that the best source from one of the best sources that I have encountered is the RDH manuals. So that they give excellent guidelines for evaluation of the assemblies of the connections in the construction site to then give a proper risk assessment of them and then adopt the correct measures for every of them. So this is what we'll get, and this is more or less what would look like. They are proposing as well some solutions, and this is let's say the book, the guideline. And that's what it looks like. It could be any manufacturer, but this is what we give as well solutions. We can offer as well a range of products that will help the moisture control from membranes to, for example, I have it in another slide, but okay, I will get there. But this is what water management also can look like: tenting, protection of the. In this case, there's a good protection of the membranes here with the tapes. Not that good a protection of the connection here. These are good case scenarios, well, where they used these type of panels protecting the water to enter in Denmark. Also allowing some details for allowing to drain. And this is just a recap of different options, solutions that Rotorbus give also for protection, membranes and this type of cap. So also separating, giving a distance from the foundation, Yeah, these are more or less products in our range that can help you avoid moisture and thus hydrogen absorption. Details, so of course, other examples, water deflection, of tenting, and it's just to give you some hints on where to go. An important thing is that moisture control plan is becoming norm, becoming law in Europe. There's going to be the Eurocode part 9 that will give the Eurocode 5 part 9 the execution standards, and they will start requiring moisture control plans. And they will be focusing a lot into the wood performance, into the wood moisture content in production and in the building site, and with a special focus on the screwed connections, especially steel to timber connections, asking for a tightening torque smaller than the characteristic breaking torque. I would say these are still broad prescriptions, but necessary, and they are starting to arrive. Finally, what I think could be a good hint for any of you that's a designer or a contractor on how to evaluate, how to address this type of this challenge, let's say, would be, okay, then what do I do? So our idea would be to elaborate a risk assessment matrix and check pair, depending on the conditions where you're at or the connection. You could find you could find yourself in a low to high risk case. So in these are all the factors that could give you a low or a medium risk. So for example, in case of the hardness of the screw, the lower risk would be 360, wood to wood, softwood connection, and so on. So dry conditions, etc. But when you start having in medium risk, when you are in wood to wood hybrid, so softwood and hardwood hybrid, wood to wood, or thin metal plates, then you start having a medium risk. And finally, steel to wood, especially with thick metal plates, would be the higher risk. But evaluating and putting them together doesn't necessarily mean that having one high risk factor would mean that the connection is a high risk connection. So this is just an idea. You could give a value. So for example, if you consider that this one count 1, this one count 2, and this one each one count 3, like the value. When you sum all of them, so you find yourself in a low risk, for example, a high risk connector, but hardness, but low risk type of connection, because you are wood to wood connection with no or correct installation in dry environment, dry conditions. You could even that type of connection would even give you a low risk assessment. So the concept of this is giving a value for each of these factors, and then accordingly using more performing material, more corrosion resistant material, or protecting the screw, protecting the connection, for example, with membranes or with mostly with membranes. So taking the considerations for reducing the risk of all those 3 factors. What do we do? In the case of our fasteners, they are, if not the most, they are one of the most certified assessed products. So in 2009, we got the first German approval. And from then, we start having the Europeans approval from 2010. In 18, we have the Japanese, US in 21, UK 22, and last year we got the Canadian. Those aren't just like stamps in a label. They are all independent assessment bodies that frequently and periodically ask us for the values and test our product to be compliant, and test many of the relevant parameters, mechanical and non-mechanical parameters. So this is just to give you an idea on the quality control of our product. And then let's talk about the CSA. Let's talk about the requirements in the Canadian standard, the new Canadian standards that was published last year, and that will become obligatory I don't remember if it's 2 or 5 years, actually. You need to forgive me because of this. Anyway, it's gonna become mandatory from some point. They require 380 vickers, so they shall not be higher than 290 vickers. We know from the chart that we saw before why this is important, because it's the stability of the screws, and asking as well for the ISO 15330, which is the continuous load test as part of the quality control process of the production, if the screw is greater than 360 vickers and below 390 vickers. So this is what the norm, at least the Canadian one, is the first one requiring this. And we are, it started from last year. We are starting as Rotoblas transitioning of all our fasteners to comply with the Canadian standards, and we can offer as well upon request. You can ask us for meeting these specific requirements. As you saw before, as you saw from this presentation, I hope this is clear. It doesn't only depend on the material. It depends on many factors. Failure depends on many factors. So yes, we're moving into the direction of reducing the risk as much as possible for our screws. But this is a complex matter that requires taking the steps from all sides. And this is what this final slide also talks about. So in all of this, premature failure causes, which is the, I wouldn't say responsibility, or I would say the bigger side of the responsibility stands. So correct me if I'm wrong. As I said, this is my understanding and my opinion on it. But installation over stress depends mostly on the installer. Sometimes the designer can put a specification where there might be an error, or the specifications are not up to date. But generally, it's up to the installer when it has let's say at least the installer has the power to overstress or not overstress. The case of internal hydrogen embrittlement, as it is very much linked to the absorption of hydrogen during manufacturing, I would say it's very clear that it's manufacturer's responsibility mostly. And then we have installation overstress and wood swelling and hydrogen embrittlement. So installation overstress and wood swelling, it's something in between designer and installer. It depends on how of the overstress factor and the swelling factor are considered in the design phase. But also it depends a lot on the construction site and the protection that's given to the connections, which can be prescribed by the designer, but also depending on the installer, sometimes are independent on the designer. So this is an issue where these two roles need to be, let's say, need to collaborate a lot. Finally, environmental hydrogen embrittlement, which is let's say the main character of today's presentation. It's mechanism of failure that depends on all three of us, manufacturer, designer, installers. Because of course, as I said before, we could even give the lower risk possible for the lowest risk possible for the fasteners, but given the right conditions of moisture presence and the right conditions of install on overstress, which can be produced during installation, then premature failure can still happen. And
Thank you so much, Andres. It was very informative. I do have some questions on the chat. I know we went over the time, but I'm gonna ask here. Can you talk more about the C4, the coatings, and the role that they play on surface treatment of the screws, and if they do prevent hydrogen embrittlement somehow? And then if the Evo coated, is this below 390 vickers, or what is the hardness of the Evo coated?
Okay, so environmental hydrogen embrittlement, or cathodic hydrogen absorption, which is the absorption of hydrogen via corrosion, starts happening when we get to the steel. So when we have already, when the corrosion process has already reached the steel, so you have eaten, let's say, there's no longer more coating, but you have reached the steel. Then hydrogen starts happening. So the more performing the coating is, the less of a likelihood of hydrogen absorption there is. Thus, then the likelihood of failure from a hydrogen embrittlement. So that's why the coating, the proper coating selection, or even selecting having a higher safety factor given by the coating is relevant. In the case of our Evo screws, concerning hardness, it's very similar to the rest of our screws. So we are in a transition period where we are lowering the hardness of everything, and we can have Evo coated screws upon request below any threshold, and but currently it's an upon request service. So we still have some Evo coated screws that can be above 360 liters or even 290 in some cases. But yeah, it's the condition of every of, let's say, of most of our screw given the transition period that we're in.
Okay, great. And one last one, what inspection programs are in place to ensure proper installation on site? Any code guidance or inspector qualifications right now seem to be very limited on this regard. So do you have any recommendations for people on the site or designers to put something on the specifications to be fully understood and addressed?
Currently, and I would say unfortunately, currently, it is up to the manufacturer. So the manufacturers will, let's say, to handle the issue. So at least in our case, we give installation instructions precise for some products, like our 4-liter screws, like our metal plate screws, and we have a smart book, and we are working on developing guidelines. But I would say the market situation or the sector situation, it's pretty much some manufacturers are working to give some design, some guidelines. I would say the only normative approach that I know of is the new Eurocode 5 execution standards that will give it's a step further into regulating the execution. I would say it's a very good step forward. And I pretty much look forward for as well, not only manufacturers working together, but working with also some I'm missing the name, but groups, associations of installers as well that give that create guidelines for proper installation. In the case of our guidelines, part of the feedback, part of the content that's there comes from feedback from our clients and from manufacturers that we know from experience. So it takes into consideration that as well. But I gotta say, this is the current state of the market.
No, that's awesome. And just one thing to add, from this question, we're gonna have a white paper like addressing more or less the summary of this content, and also any potential, let's say, measurements or mitigations. Let's say it is supposed to rain on Friday. What do you do on the construction site if you have to change your connections installed in order to have moisture content close to the real case? So we're gonna have some discussions on that. And then there is one more question regarding the slides, if it's going to be available.
If the slides are going to be available, I think they will.
Yes.
I don't know, Milvio, yes, of course. I think for the assistance of the participants of the courts, they will be.
Okay, and then the last question, how many contractors do you find seeking training or understanding these issues? On a similar note, please remind us what factors, installation angle, excess moisture, etc., are included in the prescribed reduction factor and what should be addressed as part of the engineered judgment.
Can you repeat the first one?
Yeah, so how many contractors do you find seeking training or understanding these issues or trying to really navigate on this topic? And then
I would say,
second...
like I will then ask for the next one. Sorry, Emilio. It depends on the level of how big the contractor is. So we have seen that very big contractors that have very big projects and they have very strong quality control and execution control. They tend to be more aware, because the bigger the project, the bigger the construction site, the more possible is that these failures happen, because you have thicker plates, you have bigger screws, so of course, and you have longer times. So you generally have faced this problem, and they are very keen to receive some information. Okay, what can we do to improve? So on the other side, small framers care very little, and it's a generalization. No, yeah, I wouldn't say they care little. They all care little, but it's a less of a relevant issue, because they do not face a lot of the things. So in many cases, the overstrength of the screw and the fact that or the how quick the construction sites are, then these type of failures don't tend to happen. So I would say it depends on this. Do you remember can you remember me the second question, Emilio?
Yeah, so the second part is more on the engineering side. So for example, installation angle, excess moisture, over torque, those kind of parameters, are they included in the prescribed reduction factors, or they should be included as an extra for the engineering for the engineers?
That's a great question. They are not included. They are, I would say, there are two approaches that I know of: the Canadian approach and the European approach. The European introduces the K mode, which is a factor that goes from 0.6 to 0.9, depending on the design exposure to moisture. So you would, from 0.6 from 1, you would add a safety factor that would depend on moisture. So it's a number, 0.6. Yeah, but the conditions that are given in the code are all concerning this the design products of the service life, not the building side. So it would be up to you to add another safety factor on top of it. And the Canadian approach is different. They have a little bit more detailed the swelling things, but I'm not that. I do not feel I know that much to explain it, but it's a little bit, it goes a little bit further. Of course, it's a newer norm, and it considers the swelling effect as an individual factor, but I wouldn't say it's that it takes into consideration everything that we have seen. Concerning execution, I would say there's nothing. From what I know of, there's nothing except from the safety factors that are included in the product and in the design loads that we give in the technical data sheets. So when we give you a shear capacity, it's a characteristic shear capacity many times. So it is, the statistical 5 percentile of the load. So there is a safety factor there. Then there is for the torsion capacity, the recommended torsion capacity we give is 1.5. So there is a 1.5 factor to the ultimate capacity. So there are some safety factors that are inside of the product, but from the designer side, they do not use them. So I mean, they just take the value that we give. So there's no added safety factor in the design, at least not considering the codes. Of course, you are free to add everything you want in the calculations at the end, but there's no parameter itself that would tell us you need to add. If you have some uncertainties of the builder, you need to add a safety factor for execution. Not yet.
Awesome. Thank you, Andres, for the presentation today, and thank you everybody for attending. Just want to add that this webinar on hydrogen embrittlement in screws will be going on again in February, March, and April. And those dates will be published back on our Eventbrite and social media platforms very soon. for the next 2 weeks, we do have more webinars coming up. Next week, specifically on timber connection technology as it results to connection building solutions from Rotoblast. And then the week after, the last week of January, we have a digital design tools in modern timber construction webinar. So we look forward to hosting you again soon. And thanks again for joining us today. Thank you, Andres.
Thanks to you guys.